So again we have to use the same method. Let us consider a small portion of this rod, okay, having length dx and charge dq. Now we have to write the vector form.
We didn't use the vector form in the last question.
If vectors are of same direction, we can simply add the magnitudes, but that is not the case idea, right? The force equals the charge multiplied by the electric field theta, angle subtended by the arc at the center. See, as a particular case, in the last class we were talking about electric field due to a point charge. See, we have a point charge here. So we need to find the electric field due to this charge at a point at a distance r from it. We have the formula kq divided by r squared. See, q is the charge of the object and r is the distance between this charge and that point. So we have the formula for electric field due to a point charge. But what is a point charge? The size of the object is very small compared to the distance. The object is so small that the geometry of the object can be ignored. We can consider this to be a point. But what if you have an object of bigger size? So now this is no more a point charge, so we can't ignore the geometry of the object also. So now how to find the electric field due to this point charge? Can the same formula be used? The charge of the object is q, so kq divided by r squared. But what is r? R is the distance between this object and that point. But is that defined properly, the distance between this object and that point? See, different points on this object are at different distances from that point. So which one will you take as the distance r? Or which point will you consider?
The center of mass?
No, the center of mass concept doesn't work here. See, the center of mass doesn't even represent the mass of the object, let alone the charge. See, these inverse square laws like the Newton's law of gravitation or Coulomb's law, they don't work with the center of mass because the relation is very complex, not simple linear relation. So this relation is complex, so we have to use the concept of integration. So we will consider a small part of this object, okay, very small portion having charge dq. The charge of the entire object is q, so only the small portion having charge dq, okay. This can be considered a point charge now because this is very small, so we can consider this to be a point charge and find the electric field. So for a point charge, we know how to find the electric field. So let us find the electric field due to this point charge, and using integration we can find the electric field due to the entire object. Alright, so let us use the method of integration to find the electric field. Okay, yes. So we'll find the electric field due to that small elemental portion that is denoted by dE vector, not E vector, dE vector, because it is only due to that small part dq. So dE vector. After integration we will get the value of E, which is the electric field due to the entire object. First let us write the electric field due to the charge dq. So what is the formula? Kq divided by r squared. So kq, but q here is dq, that is the charge of that small part, right? dq is the charge. So kq divided by r squared. R is the distance, so that is known. So this is the magnitude of the electric field due to the charge dq. Alright, now we need the vector form, right? dE vector. So vector, that means you multiply this by the unit vector along the direction of the electric field. So that is taken as r cap. So that is the unit vector, okay, along the direction of the electric field. But this is different for different parts of that object, right? If you instead of this portion, so if you take a different part, that will have different directions. So this is not a constant value, so it is a variable direction. And also this r is a variable, not fixed. So r is a variable. And now we have to do the integration to get the required answer. So we need E vector. That means simply integration. So integration of this. So k dq divided by r squared r cap. So that's also, this integration will give you the electric field due to the entire object. But the problem here is, so we are doing integration with respect to the variable q. But r is also a variable, so we can't do this integration directly. So we either have to convert this variable r in terms of q or q in terms of r. So our aim here is to make this integrand in terms of just one variable. Alright, so you convert this integrand into a one variable expression, so then we can find the integration. So once the integration is done, so that will give you the electric field due to the entire object. Okay, so this is the method we are going to use to find the electric field due to objects of various sizes and shapes. Alright, so now the first one here is, so here we first find the electric field due to a linear charge distribution. What is linear charge distribution? The charges are distributed along a straight line. For convenience, we call it a rod. So rod means a straight line, a linear charge distribution. See, this rod has some charge. Now we need to find the electric field due to this rod at a point on its axis. What is axis of this rod? That is simply a straight line along this rod. Our point is there on this axis. Now we need to find the electric field due to this rod at that point, which is at a distance r. This r is not same as the value of r that we use in the formula of electric field, kq divided by r squared. This is only the closest distance. Different points on the rod are at different distances from that point. So we can't use the direct formula kq divided by r squared. So we have to use the method of integration. Let us take a small portion of this rod, right? So of length dx. So dx is very small, so that we can consider this as a point charge. Do you understand? Very small, a point charge. So this has charge dq. So dq is the charge of only this small portion. So this is a point charge now. So we can find the electric field due to this point charge. So that has the direct formula. Then using integration, we can find the electric field due to this entire rod. Alright. So let us find the electric field due to this small portion having charge dq. Alright. Yes. Now, so let us find the electric field, and that is denoted by dE. So this is the electric field only due to the charge dq, alright, only for the small portion. So that's why we denote this by dE. After integration, we can get the value of E, that is the electric field due to the entire rod. So what is dE? So that is the electric field due to point charge, that is kq divided by r squared. But q here is dq, that is the charge of that, okay, small elemental portion. So that is k dq divided by r squared. R is the distance between that charged part and that point. So that is taken as x here, not r. X is the distance, so that is x squared. Alright, so this is dE. So that is the electric field due to that small portion. Now we need to do the integration to get the electric field due to the entire rod. Alright, so let us do the integration. But before that, we have to write dq, right? So what is dq? The charge of that small portion having length dx. So this is where we need to use the concept of linear charge density. What is linear charge density? So linear charge density, because the charge of the object is not given, but the linear charge density is given here. So that is denoted by lambda. So lambda is the linear charge density. That is simply the charge per unit length. Charge per unit length. 1 unit length of the rod has what amount of charge? So that is called this lambda, that is linear charge density. So lambda equals charge divided by length. So that means if you want the charge, so that equals lambda multiplied by length. Okay, so if you know the linear charge density and we need the charge multiplied by the length, so that's it. Now we need the charge dq. So what is charge? Lambda multiplied by the length. So that means this will become k. So this is lambda multiplied by the length. What is the length of that part of the rod? So that is dx. So that means lambda dx. That is the charge of that part of the rod. So lambda dx divided by x squared. Okay, so this is dE. Now we need to do the integration to get the value of E. Alright, so E here equals, so the integration, so this is k lambda, which can be taken out. So integration of, so 1 divided by x square dx. Now we need to write the limit of this integration. What is the lower limit? So x starts from r, right? So r is the minimum value, right? Minimum distance, so that is r. And this end has value r plus l. L is the length of the rod, r plus l is the total length. So r plus l. So let us do this integration. So this is simply k lambda, the integration of 1 by x squared, so that is minus 1 by x. You can also write it as x to the power minus 2, and we can do the integration. So this is the integration of this. Then the limits are r plus l. So if you simplify this, we get this is 1 by r minus 1 by r plus l. Okay, so do the simplification. This is r plus l minus r, so that is l. So k lambda l divided by, so this is r times r plus l. So that's all. So this is the electric field due to that rod. That's all. So this is remembered as a formula of electric field due to a linear charge distribution. Okay, now we can also write the formula in terms of the charge. Suppose instead of lambda, that is linear charge density, if you are given the charge of the rod, so that can also be written. What is lambda L? So lambda L is the charge density multiplied by the length, so that is the total charge. So you can also write it as kq divided by r times L plus r. So both are same, so you can also write it as kq divided by r times L plus r. If you know the charge of the rod, you can use this formula, or if you know the linear charge density, you can use this formula. So this is the first formula that you're supposed to know, the electric field due to a linear charge distribution. That means electric field due to a rod at the axial point. Do you understand? So this is one formula for electric field due to a linear charge distribution. Alright? Yes. Here also we will find the electric field due to a rod, that means a linear charge distribution, but not at a point on the axis, but at a random point, okay, at some point here which is at a distance r from this rod. So the perpendicular distance, that means the closest distance is r. Now, so again we have to use the same method. Let us consider a small portion of this rod, okay, having length dx and charge dq. Now let us find the electric field due to only this small elemental portion. Then after integration we will get the electric field due to this entire rod. So let us take this values. This distance is taken as x and this height is taken as r and this value is y, and the angles are taken as alpha and beta. So using all these measurements, let us find the electric field due to this small portion. So that is denoted by dE vector. Okay, so dE vector, so that equals k dq divided by that distance. So that distance is y squared. You understand? So y is the distance between the point and the charge. So k dq divided by y squared multiplied by r cap. R cap is the vector along the electric field. So that also we have to multiply. What is the vector along this electric field? So that is, see, that vector makes angle theta with the vertical, right? So theta with the vertical. That means the vertical component is that multiplied by cos theta, right? The vertical component is cos theta. Similarly, the horizontal component is sin theta. So sin theta I cap, cos theta j cap. Alright, so sin theta I cap plus cos theta j cap. So this is the vector along the electric field. Alright, so we have to write the vector form. Is that okay?
But we didn't use the vector form in the last question.
Yeah, in the last case we only used the scalar form of the electric field, not the vector form, because we wanted electric field at a point on the axis. You take any portion of this rod, that will have electric field in the same direction, right, the forward direction. So that means we can simply add the magnitudes of the vector. If vectors are of same direction, we can simply add the magnitudes. But that is not the case here. If you consider different parts of the rod, so that will have different directions of electric field. So we have to find the vector sum. That's why we consider the vector form. This is the unit vector along the electric field due to the charge dq, unit vector. So we have to consider vector form because these vectors are of different directions. Do you understand? Yes. So this is the vector form of the electric field due to the charge dq. Okay. Now, so this dq should be written now. So what is dq? The charge of that small portion having length dx. So same as the last case. So here also we will write. So this is k. So what is dq? That is lambda times dx, right? The linear charge density multiplied by the length. So lambda times dx, that is dq, divided by y squared multiplied by the same value sin theta I cap plus cos theta j cap. Okay, now we have to do the integration to get the answer. That's it. But the problem here is we have three variables. X is a variable here, y is a variable, and theta is a variable. Obviously we can't do this integration. We want to get all these variable in terms of one variable. So how will you write this x in terms of any other variable like theta? So let us write x in terms of theta, y in terms of theta. So we'll get integrand of a single variable, right? So let us write x. So what is x here? From that right angle triangle, so it's a right angle triangle, right? So let us take tan theta. So use some basic trigonometry. So tan theta here is x divided by r, but r is a constant, so that's not a problem. So tan theta is x divided by r, so that means x equals, say, r tan theta. Okay, now we want dx. So let us differentiate this. So dx equals r tan theta derivative is secant square theta d theta. Okay, so dx is formed. Now similarly, we also need the value of y in terms of theta. So let us find using the same right angle triangle. So y here equals, or you take say cos theta. So cos theta here is r divided by y. So which means y is equal to r divided by cos theta. So that means r secant theta. So that is the value of y. So that's it. So we found the value of dx and y in terms of theta. So let us substitute here. So this will become k lambda, so dx. So dx here is r secant square theta divided by this y square. Y square is r square secant square theta, and so d theta here. So sin theta I cap plus cos theta j cap d theta. Okay, so that's it. Now let us simplify this and do the integration. So this is secant square theta, that gets cancelled, 1 r gets cancelled. So this is simply k lambda divided by r. K lambda by r. This gets cancelled. So sin theta I cap plus cos theta j cap d theta. So this is the value of d e vector. But we want e vector, right? So let us do the integration. So this is e vector. So let us do the integration. But what is the limit of integration? Okay, what is the lower limit? See, this theta is the angle made with the vertical line. So that side we have angle beta, this side we have angle alpha. So it starts from beta to alpha, but beta is in the opposite direction. So we have to take minus beta. So opposite direction. So theta is in the clockwise direction. So that side it was beta. So this side here it is alpha. That means minus beta we have to take, because opposite direction. So minus beta, and the alpha is in this direction, so that is plus alpha. So beta minus beta to alpha. So this is the limit of the integration. So shall we do this integration here? So it is k lambda divided by r. So sin theta integration is what? Minus cos theta I cap. This is sin theta j cap. And the limits, so minus beta to alpha. Okay, so that's it. Simple substitution of this upper and lower limits. So they'll give you, so k lambda divided by r. So if you substitute the upper limit, so minus cos alpha minus cos beta. So that can be written as cos beta minus cos alpha times I cap. Similarly here, sin alpha minus sin of minus beta, that will become plus sin beta. Okay, so j cap. That's all. So this is our required electric field. So this is the formula for the electric field due to this rod at a point, okay, at a random point. So all these values are known, alpha, beta, everything. So that's all. So this is the x component of the electric field. Alright, so that is the y component of the electric field. So if you want to write it separately, so let me write it separately. Ex. Ex is the x component of the electric field. What is that? K lambda divided by r multiplied by cos beta minus cos alpha. And similarly, y component of the electric field. So Ey. So that equals, so k lambda divided by r multiplied by, so sin alpha plus sin beta. That's all. So this is the formula that you have to remember. So electric field due to a rod at a random point. Okay, this is the x component of the electric field. This is the y component of the electric field. Okay, so when you say x component, that means it is the parallel component. Okay, parallel to the rod. Okay, and y means perpendicular to the rod. So not necessarily it is horizontal, vertical, because we have taken the horizontal rod. If you have taken the vertical rod, it will be the other way around, right? So this will become the vertical component, this will become the horizontal component. So the horizontal component, so that is Ex. So that has value, this one, k lambda by r cos beta minus cos alpha. Similarly, the vertical component has electric field, the value electric field value k lambda by r sin alpha plus sin beta. You understand? So this is the formula for the electric field due to a linear charge distribution at a point, not on the axis, at some random point. Is that okay? Yes. As a particular case of what we derived previously, we will find the electric field due to an infinitely long rod. What is an infinitely long rod? Is there anything that is infinitely long? See, it is only a relative term. So the length of this rod is very big compared to the distance. So that's all. See, if you keep on increasing this length of this rod, okay, this value will increase. So that means the angle will also increase. So finally this length becomes infinity. That means the angle becomes 90 degree, right? Alpha becomes 90 degree, beta becomes 90 degree, which means it is a very long rod. So that is the meaning. Compared to the distance, this length of the rod is very big. That's what we call by the name infinitely long. There is nothing as such is infinitely long. So this is a long rod compared to the distance. So that means alpha becomes 90 degree, beta becomes 90 degrees. In that case, the length of the rod becomes very big compared to the distance. So what is the electric field in that case? So electric field due to infinite rod. So that means this alpha becomes say 90 degrees, beta also becomes 90 degrees. That means what is the electric field in the horizontal direction? So Ex becomes cos 90 and sin 90, cos 90 only again. So alpha is 90, beta is 90, so that means that becomes 0, Ex becomes 0. So which means the no electric field in the horizontal direction. That is kind of obvious, right? Because see, there is electric field in this direction, there is electric field in the opposite direction. They cancel each other by symmetry. This side and that side, it is symmetric. That means so these two electric fields cancel each other. So the net electric field is 0. Okay, the horizontal direction. Now what is the electric field in the vertical direction? So Ey. So that equals, now substitute alpha and beta 90 degrees. So that will become k lambda divided by r multiplied by sin 90 plus sin 90. So sin 90 degrees. So that is 1. So 1 plus 1, 2. So that's all. So this is 2k lambda divided by r. So that's all. So this is the electric field due to an infinitely long rod. So only the vertical component, so that has some magnitude 2k lambda divided by r. So okay, so that's all. So this is one thing that you have to remember. Okay, yes, that is electric field due to infinitely long rod. Okay. We also need to find the electric field due to a semi-infinite rod. So what is semi-infinite rod? So this angle alpha is reduced, okay, reduced to 0. Okay, finally alpha becomes 0, which means this end of the rod coincides with the midpoint. Now this beta is increased to 90 degrees, which means the other end reaches infinity. Only one end reaches infinity, the other end is at a finite position. Do you understand? So this time what happens, we call it a semi-infinite rod. See, these terms are only for our convenience, right? Semi-infinite rod, infinite rod. So we just have to understand that it is a very long rod from one side. Okay, so that's what we call by the name semi-infinite rod or infinite rod. Otherwise, as such, there is no such thing as infinitely long object. Okay, now infinite rod, so that is done. Now we have a semi-infinite rod. That means only one end reaches infinity. So in that case, what happens? The angle alpha becomes 0. Okay, alpha is 0 and beta is 90 degree. Okay, alpha becomes 0, beta is 90 degree. Just substitute in the same formula, we'll get the electric field in the x direction. So electric field in the x direction. So that equals, substitute alpha 0. That means cos beta is cos 90, that is 0, and cos 0 is 1. So that will become minus k lambda divided by r. That is electric field in the horizontal direction. What is electric field in the vertical direction? So Ey. So that equals, so again you substitute this value. So sin 90 is 1. So sin 0, so that is 0. So that means that will have value k lambda divided by r. Same thing. Okay, so that's all. So this is the electric field due to the semi-infinite rod in the horizontal and vertical direction. But if you observe, but both values are same, right? The magnitudes are same. Which means the electric field, what is the direction of this electric field? It has a vertical component, k lambda by r, vertically upward component. There will be a horizontal component in this direction, there will be a horizontal component, but that has the same magnitude, k lambda by r. Vertical and horizontal components have the same magnitude. That means the electric field, the resultant of these two will be exactly in the middle, right? That means it will make angle 45 degree. So remember, it will be the electric field due to a semi-infinite rod will be making angle 45 degree with the horizontal away from the rod. If the rod is positively charged, the electric field will be away from the rod but making angle 45 degree. Alright, this is one important concept about the electric field due to a semi-infinite rod. So that's all. So this is one formula so that you have to remember about electric field due to semi-infinite rod. So these two are particular cases of the previous formula that we have derived, electric field due to a rod at any random point. So this is a particular case where both the ends reach infinity. Here one end reaches infinity. Alright, so these are formulae that you have to remember about electric field due to linear charge distribution. Okay. Here we'll find the electric field due to a ring of charges. Here the charges are distributed over a circle. So we need to find the electric field due to these charges at a point on the axis of the circle. What is axis of the circle? Just a line passing through the center and perpendicular to the plane of the circle. Alright, so this is the axis. Now we have a point at a distance x from the center. So we have to find the electric field due to this ring at that point. Alright, as usual we will consider a small portion of this ring, say dq, the charge is dq, and let us find the electric field due to the charge dq, and then using integration we'll find the electric field due to the entire ring. Alright, the same method, say dE. So dE is the electric field due to only that charge dq. So that equals, so same formula, that is kq divided by r square. So k dq here divided by r is the distance. So that distance is taken as y. So y square. Okay, this is only the magnitude, but we also need the vector here, right? We want the vector form because this direction is different. So this E vector makes some angle theta with the horizontal. So we have to write the vector form. But let us avoid using this vector form because this E vector has two components, one in the horizontal direction, one in the vertical downward direction. You understand? Horizontal component and vertically downward direction. But this vertically downward directions will cancel each other. See here, you take the topmost point. It will be a vertically downward component, and if you take the bottommost point of the ring, so there will be a vertically upward component. This downward component and upward component cancel each other, so there will be net zero component in the vertical direction. So downward component, upward components cancel each other. There is no vertical component. We will only be left with the horizontal component. So we don't need to consider the vector form. You only consider the horizontal component, right? Only the scalar form. You understand? We can also consider the vector form. Just to make it easier, we will cancel out all the vertical components. We will only use the horizontal component. Do you understand? For every vertical component, there will be an opposite downward vertical component. So they cancel each other. So we will only be left with the horizontal component. So let us take the horizontal component. So this multiplied by cos theta, right? Horizontal component. E cos theta. That's all. So this is the electric field due to that charge dq. Okay, now let us do the integration to find the electric field due to the entire ring. Okay, but let us write the value of cos theta. So y value can also be written in terms of the given values. So what is the value of y? So this is k divided by, so it's a right angle triangle, right? So you can use Pythagoras theorem to find the value of y, the hypotenuse, that is x squared plus r squared. Okay, y square equals x square plus r square, and even cos theta can be found using the same right angle triangle. So cos theta here in that triangle is x divided by y. So y is again square root of x square plus r square. Now we'll use the integration to find the electric field due to the entire ring. So dE is given. So now E is just the integration. So kx divided by, so this value x squared plus r squared to the power 3 by 2. See, remember these values are constants. So x is a constant here. So that is fixed here. Okay, for that particular point x is fixed, and r is also a constant, the radius of the ring. So everything is a constant. The only one variable is dq. So that means all this can be taken out. So this is integration of dq. So it is very easy to do the integration. What is integration of dq? That is q, that is the total charge. So simply we get the answer, that equals k q x by x squared plus r squared to the power 3 by 2. Okay, that's all. So this is the electric field due to that ring. You understand? So this is the formula that you have to remember. So the electric field due to a ring of charges. So this r is the radius of the ring. So this x is the distance from the center of the ring. Okay, so that distance is x. So this formula you have to remember. So the electric field due to, okay, so that's all. So this is the next formula about electric field. So a ring of charges. Okay, so that has electric field simply kqx divided by x squared plus r squared to the power 3 by 2. Okay. Here we have a charged disk. The hollow part of the ring is filled now. It is a surface here. So we need to find the electric field due to this surface, not a line or a curve. It is a surface. So we need to find the electric field due to this disk at a point on the axis, just like the last case. So let us find the electric field due to this disk. But for that, we will consider a small ring having thickness, say dr, of radius r. See, this is a ring, okay? It means it is like a circle but having some thickness. So dr is the thickness and r is the radius. This is more like a ring now. So we know the formula for the electric field due to a ring. So that formula can be used, and then after integration we will be able to get the electric field due to the entire disk. Alright, let us find the electric field due to the ring. So that is denoted by d. So that is kxq. Q here is dq, that is only due to that small portion. So that is dq divided by x squared plus r squared. So x squared plus r squared to the power 3 by 2. So this is the electric field due to a ring. So that's what we derived previously. So that means, so this is the electric field due to only that small portion. So that is in the shape of a ring. Now what is dq? dq is the charge on that ring. Alright, here it is a surface. Remember, it is a surface. So we have to use the concept of surface charge density. So what is surface charge density? Surface charge density, just like the linear charge density. What is linear charge density? Lambda. So that is charge per unit length. Similarly, the surface charge density denoted by sigma. So that is the charge per unit volume. Sorry, area. Area, right? The surface. So area. So charge per unit area. So that is called surface charge density. So that is denoted by this sigma. So now you tell me what is dq? So dq is the surface charge density multiplied by area. But what is the area of that ring? Okay, that small portion. So that has some thickness, right? dr. So what is the area? So we can use the area of the circle. See, the outer radius of the circle is r plus dr, right? R plus dr, that is the outer radius. The inner radius is r. So you find the area of the outer portion and minus the area of the inner portion. So that will give you the area of that thickness. Alright, so let us find. So what is the area of the outer portion? So that is pi, the radius square. Radius is r plus dr square, minus the inner portion as radius r, that is pi r square. So that means this is pi r square. So if you simplify this, this is sigma pi. So this is r squared minus r squared, that gets cancelled, and then 2r dr plus dr square. But we usually ignore this dr square, right? So higher powers of dr, because dr is already very small, so we ignore the higher powers of dr. So that means dr square, so we need not consider. So 2r dr. So that's also, this is the value of dq that can be substituted here. See, you can also find this area using another method, like so if you cut this strip across and you stretch it, it will become a rectangle, right? So the thickness is dr and length is 2 pi r, so 2 pi r dr. So that is another way to find it. So this is also okay, right? So you find the outer area minus the inner area, that will give you the area of only the thickness. Okay, that's all. We found dq, so that can be substituted here. So this will be simply kx dq. So dq is sigma pi 2r dr divided by x squared plus r squared to the power 3 by 2. Okay, so that is dE. Okay. Alright, so now we have to do the integration to get the value of E. Okay, remember here x is a constant, r is a variable, r is a variable, because the radius of that ring is not fixed, right? If you increase the length, so that will cover the entire disk. So r is the variable here, so x is a constant, so we have to do this integration. Okay, let us do this integration. So E here equals, so this value is kx sigma pi 2r dr divided by x squared plus r squared to the power 3 by 2, and then integration. R ranges from 0 to capital R, right? So 0 is at the center, and the radius of the entire disk, so that is capital R. So that means R is from 0 to capital R. Okay, so let us do this integration. But how will you do this integration? So we use the simple substitution method. One method is the trigonometric substitution. You can substitute this r equals x tan theta, because 1 plus tan square theta can be written as secant square theta. The square root will be removed. That is one way to do it. Otherwise, we can simply do a direct substitution, because the derivative of this part is 2r dr, that is there already. So 2r dr. So let us make use of direct substitution. You take x squared plus r squared equals some new variable, say t. So let us assume that some t equals, so x squared plus r squared. Now let us find dt. Okay, let us find the derivative of this. See, let me take the value of this as t squared. You can also take t squared. T is also okay, t squared, because already power is 1 by 2. T squared will make our calculation a little easier. So let us take this as t squared. So that means what is the derivative? So this is 2t dt. That equals, this is a constant, so 2r dr. So 2r dr equals 2t dt. We already have 2r dr, so that can be replaced by 2t dt. So this integration will become now, so kx sigma pi. So this will become 2t dt divided by, so this value x squared plus r squared, that's what we have taken as t squared. So t squared to the power 3 by 2, so that is t cube. And integration, and the limit will also change. See, when x is 0, sorry, r is 0 initially. So when r is 0, t is same as x only. And when r is capital R, when r equals capital R, then t value is square root of x squared plus r squared. So this value is square root of x squared plus r squared. So let us do this integration. So 2 can be taken out. So this can be written as 2kx sigma pi. This 1 divided by t square. 1 divided by t square. So what is the integration of that? So that is integration minus 1 by t. Okay, from x to square root of x squared plus r squared. Okay, so that's all. So if you do the substitution upper and lower limit, so we will get the value. So this is simply 2kx sigma pi multiplied by, so this if you substitute, so this is 1 by x square root of x squared plus r squared. Right? Yes. Now if you multiply this x inside, we'll get, so 2k sigma pi multiplied by 1 minus x divided by square root of x squared plus r squared. So that's all. So this is our required value of E. Alright, so that's it. So now we can write this k in terms of this epsilon 0, because we already have a pi, so there is a chance of this pi getting cancelled, because what is k? 1 divided by 4 pi epsilon 0, so that pi will get cancelled. So you write this k in terms of epsilon 0. So what will you get? So this will become, so this E here equals, so what is k? 1 divided by 4 pi epsilon 0. So this 2 pi will get cancelled. So 2 epsilon 0 will be left. So this is sigma divided by 2 epsilon 0. Same value here, multiplied by 1 minus x divided by root, same value, x squared plus r squared. So that's also, this is one formula you have to remember, the electric field due to a disk. Okay. So that's also, this is the electric field due to a disk that you have to remember. See, all these are simple calculations, so that we used for, see, the surface charge density. In the last cases we had used the linear charge density lambda, that is charge per unit length. Here we use the surface charge density, which is charge per unit area. So suppose we have a volume, okay, a solid object, so then the volume density, so that can be written as the charge per unit volume. So that can also be used if required. So here the surface charge density is charge per area. Do you understand? So all these are calculations which we'll use to get to the answer. Okay, so that's all. So this is our required electric field due to the disk. Okay. So here we need to find the electric field due to an infinite plane. So what is an infinite plane? See, this is a flat surface but without any boundary. It is a very large plane. So that has no boundary, but it is a flat surface. So we need to find the electric field due to this large plane of charges. Okay, so how will you find it? See, in the last case we derived the formula for electric field due to a disk, right? So this is the formula. Now if you increase the radius to infinity, okay, you keep on increasing the radius of the disk to infinity, finally it will become infinitely large plane, right?
But the shape will be circular, not rectangular.
Okay, take for example this circular disc. So this is circular in shape. Now you increase the radius, it is still circular. Increase the radius further, it is still circular. You keep on increasing the radius, it reaches infinity. Okay, the radius becomes infinity. You tell me now what is the shape of this. Is it rectangular or circular or square? So it doesn't really matter. So once the size becomes infinitely large, so this doesn't matter whether it is a circular shape or a rectangular shape. So it doesn't really matter. We can use the formula for the electric field due to a disk and increase the radius to infinity. That will give you the electric field due to a large plane. Do you understand? So what is electric field due to a so the electric field due to the disk. Okay, so that has the formula, the electric field due to a disk. So that formula we have derived just now. So that equals, this is sigma divided by 2 epsilon 0 1 minus x divided by square root of x squared plus r squared. Okay, so this is the electric field due to the disk. Now we will substitute the value of r infinity. As r tends to infinity, this becomes a very large plane. So r is infinity. So denominator becomes infinity. So this whole value becomes 0, right? Something divided by infinity. So this is a very large value. So this becomes 0. So that means our required electric field equals sigma divided by 2 epsilon 0. So that becomes 0, 1. That's all. So this is the answer. So this is the electric field due to infinitely large plane. You understand? So this is one formula that you can remember. So the electric field due to infinitely large plane. Okay, so that is the formula, sigma divided by 2 epsilon 0. So if you observe, this electric field is independent of the value of x, which means whatever is the distance, the electric field remains the same, sigma divided by 2 epsilon 0. Alright, so it is independent of the distance as long as the distance x is very small compared to the size of the plane. So this value remains same, sigma divided by 2 epsilon 0. So that is the electric field due to infinitely large sheet of charges. Do you understand? Infinite plane. So that is electric field sigma divided by 2 epsilon 0. Is that okay? Yes. Here we will find the electric field not due to the entire circle, only a part of the circle. So this is called an arc with subtends angle theta at the center. So we will find the electric field due to this arc at the center. Alright, so let us find it using the same method. Let us consider a small portion of this arc having charge dq. Let us find the electric field only due to this portion. So dq. Now let's take this angle with the vertical to be phi, and this arc, the small portion, that subtends angle say d phi. Now let us find the electric field due to this small portion having charge dq. Alright, so that is denoted by dE. So that equals, so k, q here is the charge dq divided by the distance squared. So that distance is r only, the radius, so radius squared. Alright, this is the electric field, but we want the vector form, right? Because the different part of the arc will have different directions of electric field. Alright, so now we will take the vertical component because the horizontal components cancel each other, right? Like see, this is a symmetric arc, right? Symmetric about the vertical line, which means there will be a horizontal component in this direction, there will be a horizontal component in this direction, so they'll cancel each other. We'll only be left with the vertically downward component. So you take the vertically downward component of this. Okay, so no need to consider the vector form, only the vertically downward component. Okay, so this multiplied by cos phi. So that's all. So this is the electric field due to that small portion in the vertically downward direction. Okay, done. Now we have to do the integration. But before that, what is dq? dq is the charge. So that charge of that small part. Okay, so what is that? So we have to multiply the linear charge density by the length, right? So that is the formula for finding the charge. The linear charge density multiplied by that length will give you that charge. But what is the length of that small portion of the arc? See, you have to remember this formula. So for a circle or arc of the circle, the length of the arc has the formula, this is the radius. What is the length of the arc formula? The length of the arc equals the radius multiplied by theta. If theta is in radian, so radius multiplied by the angle will give you the length of the arc. So this arc here, that small portion of the arc has subtends angle d phi, which means the angle theta here is d phi, and the radius is also known. So that means this dq here equals, so k multiplied by, so dq here is lambda, the linear charge density. multiplied by that length of the arc is r dt d phi. So this is the charge dq, so cos phi divided by r squared. So that's all. So now we have to do the integration. Alright, let's simplify this. So E here equals the integration of this. So k divided by r, 1r gets cancelled, lambda integration of cos phi d phi. Now we have to write the limit of this integration. So what is the lower limit? See, this phi ranges from, see this side we have angle theta by 2, half of the angle. See, this phi is the angle made with the vertical. So this side we have angle, half of the angle, total angle is theta. So this side we have angle theta by 2 and that side we have angle theta by 2 with the vertical. So this side in the opposite direction, so we have to take minus theta by 2 this time, plus theta by 2 that side. So which means the lower limit is minus theta by 2 and the upper limit here is plus theta by 2. So the limit here is minus theta by 2 to theta by 2. Okay, so let us do the integration here. So that is k lambda by r multiplied by, so this has integration sine phi from minus theta by 2 to theta by 2. So this has value, let us substitute this. So it is sine theta by 2 minus of minus sine theta by 2. So 2 times sine theta by 2. So that will become, so 2k lambda divided by r multiplied by sine theta by 2. So that's all. So this is the formula for the electric field due to this arc. Okay, what is the direction of this electric field? So that will be in the vertically downward direction, right? Vertically downward direction. By symmetry, so the electric field will be pointing downwards, right? But the magnitude has this value, 2k lambda divided by r multiplied by sine theta by 2. What is this theta? Angle subtended by the arc at the center. See, as a particular case, what if angle theta is say 360 degrees? If the angle theta is 360 degree, that means it is not just an arc, it is an entire circle, right? The complete circle. So what is the electric field at the center? So that will be 0 by symmetry, right? All electric fields in all directions, they cancel each other. The electric field due to the ring at the center, so that is 0. Alright, that is a particular case of this when theta equals say 360 degree. But this is a general case where arc subtends angle theta at the center, so that has electric field. So this value 2k lambda divided by r, so sine theta by 2. Is that okay? Yes. So we have done some formulae related to electric field due to various shapes like a linear charge distribution, a circular ring, a circular disc, an arc of the circle, and there are many more shapes like this, like a solid sphere, a spherical shell, a cylinder. All these things will be done later on after discussing Gauss law, but for now we just use integration method to derive these formulae. Now we will do some questions related to only these formulae. So be thorough with all these concepts, so before we start doing questions on this. Okay. An infinite rod is placed along y-axis. It has linear charge density lambda for positive values of y and minus lambda for negative values of y. The electric field at a, 0 is. Here we are given a charged rod with infinite length lying along y-axis. We need to find the electric field due to this rod at a point on x-axis. But this is not a uniformly charged rod. So the upper part of the rod has charge density lambda. The lower part has a linear charge density minus lambda. So the upper part is positively charged, the lower part is negatively charged. So we have to consider this to be a combination of two semi-infinite rods. So we have to find the electric field due to the upper part separately, the lower part separately, and find the vector sum. Alright, so let us find separately the electric field due to these two parts of the rod. So first of all, we will find the electric field due to the upper part of the rod. Let us denote this by say E1 vector. So that is the electric field due to the upper part which is charged with the linear charge density lambda. So if you remember the formula for the electric field due to the semi-infinite rod, so that makes angle 45 degree with the horizontal, right? See, this has two components, one in the horizontal direction, one in the vertical direction, vertically downward direction. So this electric field will be away from the rod because this is positively charged. That means the electric field will be away from the rod, making angle 45 degree. So this direction. So that means it has two components, horizontal direction and vertically downward direction. But these two components have the same magnitude. Do you remember the magnitude of the components of the two components along horizontal direction and vertical direction? So that has value k lambda divided by the distance, which is a. This is the component in the horizontal direction and also in the vertical direction. Okay, so what is the vector along the horizontal direction? So this multiplied by the unit vector along the vertical direction in the horizontal direction, that is I cap. So this is the horizontal component of the electric field. Similarly, we'll find the vertical component that has same value k lambda divided by a, but this is negative y direction, that means minus j cap, that is the unit vector. So this is simply I cap. If you take out a common factor, minus j cap. The horizontal component and the vertical component, so they are same. So this is the total electric field due to the upper part of the rod. Okay, done. Similarly, we'll find the electric field due to the lower part. But this time the lower part is negatively charged. That means electric field will be towards the charge, right? So towards, because for negatively charged object, the electric field will be towards the charge. So that means again still making angle 45 degree, but towards the charge. So this direction. This also has two components, one in the horizontal direction, one in the vertical direction. Horizontal direction means the negative x-axis, right? And vertical direction, so negative y-axis. So, but it has the same value, k lambda by a. So that is denoted by, say, E2 vector. So that equals, so k lambda divided by a. We are using only lambda, not minus lambda. We only take the magnitude first. So the direction can be taken into account because we are using the vector form. So k lambda by a, that is the magnitude of the components, two components. Alright, now, so this has a horizontal component which has unit vector minus I cap, and similarly vertically downward component, so that has unit vector minus j cap. So that's it. This is the electric field due to the lower part of the rod. So we have found both. Now we have to find the net electric field. So that is given by, so the net electric field, say E vector. So that is given by the sum of two vectors. So that is E1 vector plus E2 vector. So if you simplify this, so if you add these two values, you'll get, so I cap, so minus I cap, so that gets cancelled. So we'll get minus 2k lambda divided by a j cap. You understand? So if you simply add these two, so I cap minus I cap get cancelled, and minus j, this is 2 times minus j cap. So that's all. So if you just need the electric field strength, that means only the magnitude, so that is E. So take the magnitude of this, so that is simply 2k lambda divided by a. So that's all. So magnitude of j cap, that is 1. So 2k lambda by a, that is the total electric field due to these two parts of the rod. Alright, so simple. So that is the answer to the question. The electric field strength at the point A due to the infinitely long rod of the given shape with the linear charge density lambda is. So this shape is somewhat weird, but it is a combination of two known shapes. One is a semicircle, which means it is an arc. So we have the electric field due to an arc, and the other one is a rod, okay, infinitely long rod. So we have to find the electric field due to these two separately. So then find the vector sum, just like the last question. So let us first find the electric field due to that semicircle. So that is an arc, right? So the electric field due to an arc. So that we will find first. So due to the arc. So that is denoted by, say, E1 vector. So that equals, so we have the formula for the electric field due to an arc. So that is 2k lambda divided by the radius r multiplied by sine theta by 2. So theta is the angle subtended by the arc at the center. But this is a semicircle, so that subtends angle 180 degrees, right? Because the total circle subtends angle 360 degrees. This is half of the circle, so this subtends angle 180 degrees. So theta here is 180 degrees. So this is the magnitude of the electric field due to the arc. Now we want the direction also. This is a positively charged object, so the electric field will be away from that object, right? That means vertically downward. By symmetry, we can say that the electric field will have direction in the vertically downward direction, so that has unit vector minus j cap. Okay, so that's it. So this is the formula, and the direction can be understood from the geometry of the object. Alright, so now we have the electric field due to the arc. So if you simplify this, see sine 180 by 2, which means sine 90 degrees. So sine 90 is 1. So this will become minus 2k lambda divided by r multiplied by j cap. So this is the electric field due to the arc. Alright, so now we will find the electric field due to that rod, okay, but it is an infinite rod, okay, semi-infinite rod. So what is the electric field due to a semi-infinite rod?
K lambda by r making angle 45 degree.
No, that formula cannot be used here. See, we need to find the electric field due to a semi-infinite rod at this point, closer to one end on the perpendicular axis. Only then this formula works. So the electric field will be at an angle 45 degree with the horizontal, and it has two components, horizontal, vertical components. So K lambda by A. So that is the formula only when the point is here. But here this time the point is on the axis of the rod. So here. So this formula does not work. So we need to use the formula that we derived first, the electric field due to a rod at an axial point. Okay, so that formula has value. So due to this rod. So denoted by say E2 vector. So what is the formula? Remember, KQ divided by R multiplied by L plus R. KQ divided by R into L plus R. So KQ. But Q can be written as what? Lambda times L, right? So Q is the charge. So linear charge density multiplied by the length. So K lambda L divided by R times L plus R. So this R is the distance. Okay, the closest distance is R. So that's the radius. So R, L plus R. That's all. This is the magnitude of the electric field. But now we need the direction also. Obviously the direction is in the forward direction, right? So positive x-axis. So that means, so this is just I cap. Okay, the unit vector along x-axis. That is I cap. So that's it. But there is a problem here. This L is not known. So L is infinity, right? Because this is an infinitely long rod. So this L is infinity. So how to substitute here infinity? So we can just like that substitute infinity. So L here and here also we have L. So we have to use the concept of limit. Alright. So we have to simplify this. So K lambda L divided by, this is the method to find limit, right? So if you take out L, so if you take L out, so it will become 1 plus R divided by L I cap. So this time L tends to infinity. Okay. Substitute infinity after cancelling out this L. So L is cancelled now. Then we can substitute L value infinity, because this is infinitely long rod, so length of the rod is infinity. So L is infinity, R divided by infinity, right? So L is very large, so this value becomes 0. So this value becomes 0, which means K lambda divided by R. That's all. So this value is simply K lambda divided by R I cap. That's all. So here we have substituted L infinity. Okay, L tends to infinity. So that's all. So this is the electric field due to that the second part. So that is a rod, infinitely long rod. So now we have to find the vector sum of these two. So this implies our required electric field E vector. So that equals the sum of these two vectors. So it is E1 vector plus E2 vector. So that will give you the value. So if you take out the common factor, which is K lambda by R, so K lambda divided by R, if you take out, so you'll get I cap, so minus 2 J cap. Minus 2 J cap. So that's all. So that is the electric field vector. See, if you want only the magnitude of the electric field, so that can be found. So the electric field due to this. So this is a scalar, K lambda divided by R. So we just find the magnitude of that vector. So that will give you our required answer. So that is K lambda divided by R multiplied by the magnitude of this vector, the square root of 1 plus 4, right? Square root of say 1 square plus 2 square. So that is square root of 5. So that's it. So that is the electric field strength due to this charged object at that point. Alright, so that's all. So we find the electric field due to these two known shapes and then find the vector sum. That's all. Okay. A long rod of charge density lambda is bent in the given shape. The electric field at the point A is. So again the same type of question, right? So one infinitely long rod is bent in this shape. See, it's a combination of one semi-infinite rod along x-axis and one semi-infinite rod along y-axis, and also there is an arc, exactly a quarter of the circle, right? If you complete it, you get a circle. It is a part of a circle, 1/4 of the circle. That means it subtends say 90 degree at the center. So we have to find the electric field due to all these combinations. So let us find the vector sum of all these electric fields. Alright, so let us first find the electric field due to that arc. So due to the arc, the electric field is, so that has the formula. So let's say E1 vector, so that equals, so 2K lambda divided by the radius R sine of theta by 2, right? Theta by 2. What is theta here? So this arc subtends angle 90 degree at the center, because this is 1/4 of the circle, so it subtends 90 degree at the center. So that means this is 90 degrees divided by 2. Alright, so 2k lambda by r multiplied by sine theta by 2. So theta here is 90 degrees. This is only the magnitude. Now we need to write the vector form. So what is the unit vector along the electric field due to that rod? See, by symmetry, this electric field will be making angle 45 degree, right? Because it is symmetric with respect to x and y axis, right? That means, so it will be like exactly 45 degree. Right, it's exactly the middle, so 45 degree. So that means the vector along this electric field, that is I cap plus j cap, right? So this is I cap plus j cap. So this is the vector along the electric field which is making angle 45 degree with the x-axis and y-axis. But this is a vector, but we only need the unit vector because we have already taken the magnitude. We just need the unit vector. So you have to divide this by its magnitude. What's the magnitude of this vector? So root 2, right, square root of 1 plus 1. So this is the unit vector along the direction of the electric field, and this is the magnitude of the electric field. So that means, so we've got the electric field vector due to that arc. Alright, so let us simplify this. So sine 90 divided by 2. So that is sine 45 degrees. So sine 45 is 1 by root 2. Already there is root 2, so we'll get 1 by 2. So this 2 will get cancelled with that. So k lambda divided by r. So that gets cancelled, simply I cap plus j cap. So that's all. So this is the electric field due to that arc. Okay, done. Now similarly, electric field due to the rod along x-axis. So electric field due to the rod along x-axis. So that is a semi-infinite rod. So we need to find the electric field. So now, so we have the same formula. So let us take this to be, say, E2 vector. So that equals, so that is a formula. What is that? K lambda divided by that distance. So that distance is the radius only. So k lambda divided by r. So that is the component of the electric field both in the vertical and horizontal direction. But it's a positively charged rod, which means it will be away from the rod. The electric field will be away from the rod, making angle 45 degree. So one in the vertically upward direction, one in the horizontal direction. Alright, so that, but the same magnitude for both the components. So this is, so one in the horizontal direction, but negative x-axis. So minus I cap. And the vertically upward component also same. So k lambda divided by r. So the unit vector along the upward direction. So that is j cap. So j cap. So that's it. So that is the electric field due to the semi-infinite rod along x-axis. Similarly, so we'll have to find the electric field due to the rod along y-axis. So the same idea. Say if you take that as say E3 vector. So that equals, so same value k lambda divided by r, magnitude same, but what is the direction of the electric field? Now again away from that rod, okay, away from that rod, making angle 45 degree, which means it has a horizontal component in the positive x direction and vertical component in the negative y direction. So here horizontal component and negative y direction, so vertical component. So we have to write the horizontal component, which is I cap, that is the unit vector along positive x axis, and negative y axis. So that has unit vector minus j cap. So that's our I cap minus j cap. So that is the vector, okay, along which the electric field lies in. Okay, now that's it. So we've got all the three vectors. Okay, so that is the electric field due to all the three parts. Now we have to find the total electric field. So we find the electric field vector, so which is the sum of these three vectors. So if you add all these vectors, okay, so it will be right. So E1 plus E2 vector plus E3 vector. Okay, so if you add all this, what do you get? So this is k lambda by r, k lambda by r, k lambda by r. So we can take out as a common factor. So k lambda by r multiplied by, so this is I cap plus j cap. This is minus I cap plus j cap. Similarly, this one is I cap minus j cap. Okay. So if you add these values, so minus I plus I cancels and j cap cancels with the minus j cap. So this is simply I cap plus j cap. So this is k lambda by r multiplied by I cap plus j cap. So that's all. This is our required electric field vector. Okay, again, if you want just the magnitude, so find the magnitude of this. This is k lambda divided by r multiplied by, say, root 2. So root 2 is the magnitude of I cap plus j cap. So k lambda by r multiplied by root 2. So that is the answer. Okay. See, if you observe this electric field, the net electric field is only k lambda by r I cap plus j cap. So that is same as this, right? K lambda by r I cap plus j cap. So these two electric fields, they cancel each other. Say minus I cap plus I cap. plus j cap minus, they cancel each other. See, if you observe, so the electric field due to the rod or along the y-axis, so that is in this direction, and the rod along x-axis, that is in the opposite direction. They have the same magnitude, but in the opposite direction, they cancel each other. If you observe this symmetry, right, so the geometry of this, we could have avoided these steps, right. Directly we could have written the answer this one, right, because these two are the same vectors in the opposite direction, same magnitude but opposite direction, so these two will anyway cancel each other. So we could have avoided this and directly written this, but even if you do this, anyway they get cancel finally. So the answer here is simply this one, k lambda by r, I cap plus j cap, and the magnitude of that is, so k lambda by r times root 2. Okay. The distance of the point on the axis of a ring of radius r from the center at which the electric field is maximum is. We have done questions of this type in Coulomb's law and electric field due to point charge. The same type of question, we need to find the maximum electric field at a point on the axis of the ring. So we have the formula for the electric field due to a ring on its axis. Now, so this is the variable electric field, because at different points the electric field will be different. Now we need to find the point at which the electric field is maximum. Alright, so let us write the formula for the electric field, and to find the maximum, the same method, we have to use the derivative method. So you have to find the derivative, equate that to 0. So simple method. So let us find the electric field due to that rod. Okay, so that is the electric field due to that ring. So that has a formula. So E equals, we are writing only the magnitude here. Alright, so K Q X divided by, so this is x squared plus r squared to the power 3 by 2. So this is the electric field at any point, the point at a distance x from the center. Now, so this we want the maximum value of, so that means you have to find the derivative, equate that to 0. So let's find the derivative. So dE divided by dx. So let us find the derivatives. This is kq, and this derivative, so you have to use the derivative using that quotient rule, right, division. So x divided by this value, so u by v. So v squared in the denominator, so it is x squared plus r squared cube. Alright, so v squared, and here in the numerator we have v, which is x squared plus r squared to the power 3 by 2 minus this derivative is 1. So this value x multiplied by the derivative of this, so x multiplied by this derivative is 3 by 2 times x squared plus r squared to the power 1 by 2 multiplied by the derivative of this x squared plus r squared, means chain rule, right, x squared has derivative 2x. Alright, so this value is equated to 0, because for maximum value or minimum value the derivative must be equal to 0. So this is equated to 0. Let's simplify this. So we can multiply by this, you can divide by the common factor, you can divide by this x squared plus r squared to the power half. So that if you divide, you will get x squared plus r squared. Alright, so if you divide by x squared plus r squared to the power half, so it will become 3 by 2 minus 1 by 2, so that is 1. So this minus, so 2 cancels, so 3x squared. So 3x squared equals 0. So that will give you the value. So 2x squared equals r squared. So that's also, that gives the value of x, r divided by 2, root 2. R by root 2 is the distance at which the electric field is maximum. We only taken the positive value, not minus r by root 2, because that has the same distance, right? So the distance is simply r divided by root 2. This is the point at which the electric field will be maximum. You understand? So that's also, that is the answer. But suppose you are asked to find the maximum electric field. So that is simple. Once you got the value of x, so that can be substituted here to find the electric field. So if you substitute this value of x here in this expression, we get the maximum electric field. But we just need that distance, so that is simply r by root 2. So at a distance r by root 2 from the center of the ring, so the electric field will be maximum. Okay. The electrostatic force between a ring of radius r and charge q and a semi-infinite rod of linear charge density lambda placed along the axis whose one end is at the center of the ring is. So here two charged objects are given. So one is a ring, the other one is a rod. So we have to find the electrostatic force between these two charged objects. So how to find the force between two charged objects?
KQ1 Q2 divided by R squared.
Coulomb's law. What these two objects look like point charges to you? See, Coulomb's law works only between point charges. The charges Q1 and Q2 are so small that the geometry of these objects can be ignored. But these two objects are not point charges. So one is a ring, the other one is a rod. They are not point charges. Coulomb's law cannot be applied here. See, if Coulomb's law can be applied to any type of object, so where is the need to learn the concept of electric field? So we learn electric field only because Coulomb's law cannot be applied in all the cases. So these two objects are not point charges, Coulomb's law cannot be applied. So we have to use the concept of electric field. See, if not both these objects, at least one of these objects is suppose a point charge. Okay, suppose one of them is a ring, the other one is a point charge. Then we have the formula to find the force between these two objects, right? So do you remember the formula? See, suppose one of them is not a point charge, okay, so some object, but the other one is a point charge, say here. So the other one is a point charge. Then we can find the force between these two objects, but not by Coulomb's law directly, but using electric field. So let us first find the electric field due to this object at that point. So it has some electric field, say E, and this is a point charge having charge Q. Alright, now the force between these two objects is given by the formula. So the force here equals the charge multiplied by the electric field. You understand? So force equals charge multiplied by electric field. So you first find the electric field and multiply by the charge, we get the force. You understand? So for that to work, at least one of these objects must be a point charge. But here both of them are not point charges. So we have to find the force between them. How will you find? So we will use the method of
integration.
Yes, we have to use the concept of integration. So let us do this question by two methods. The first method is we will keep this ring as it is. Now we will consider only a small portion of the rod, very small portion having charge dq, having length dx at a distance x from the center of the ring. So only on this small portion which can be treated as a point charge, because the length dx is taken to be very small. So this can be treated now as a point charge like this q here. So now we will find the electric field due to the ring at that point and multiply by that charge, we will get the force due to the ring on that small portion of the rod. But we need the force on the entire rod. So we have to use integration to find the force on the entire rod. So that is the method we are going to use. Similarly, we will also do this method. See, so you will consider the rod as it is. Now we will find the electric field due to the rod and then multiply by the charge of the ring. Do you understand? First, you will find the electric field due to the ring and multiply by the charge of the rod. And similarly, we will also do by another method with the finding the electric field due to that rod and multiply by the charge of the ring. So let us do by the first method. So electric field due to ring. So electric field due to a ring. So this electric field due to the ring has the formula E equals kqx divided by x squared plus r squared to the power 3 by 2. So this is the formula for the electric field at a distance x from the center. Okay, now this electric field we need to multiply by the charge to get the force. So let us find the force. So force on the charge dq only, not the entire force, not the force on the entire rod, only the small portion dq. So that has formula. So what is the formula for force? The charge multiplied by the electric field. So the charge here is only dq multiplied by this electric field. Okay, charge multiplied by electric field. So that's it. Now, so this is df, not f. Only the small force, the force acting on the small portion, not the entire force. So that we will find using integration later, but this is only df. So df equals dq multiplied by e. Okay, so now we want f. So how to find f? We have to do the integration. So the integration of this value. So what is the value of e? So e here is kqx divided by this value, x squared plus r squared to the power 3 by 2. This is e multiplied by dq. So this dq. So what is dq? The charge of that small portion. So this is a linear charge distribution. That means the charge is same as the linear charge density lambda multiplied by the length. Lambda multiplied by that length is dx. So lambda dx is the required charge. So lambda dx. So that is the charge on the small portion of that rod. Okay, that's all. So we have to do the integration. What is the range here? So the limit of integration. See, x starts from 0, right? At the center of the ring, x value is 0. So starting at 0 and it reaches till infinity, right? It is an infinitely long rod. So the final value is infinity. So this integration we need to find. That's all. But how will you do this integration? See, we have to know this substitution, right? Trigonometric substitution. The moment you see x squared plus a squared form, so we can substitute some trigonometric expression here. So what can you substitute? X squared plus r squared. So that means you have to substitute x equal to r tan theta. Then only you will get the formula 1 plus tan square theta, which can be written as secant square theta. So substitute x value r tan theta. So that's it. Simply substitute x value r tan theta, so that its derivative will be r secant square theta d theta. So this substitution if you do here, so this expression becomes, so integration of k q x here, so lambda also, x is r tan theta, and also dx here is r secant square theta d theta, so r secant square theta d theta divided by x squared plus r squared. So this is like x is r tan theta, so r square tan square theta, r square can be taken out, so that will become r cube because the power is 3 by 2. So tan square theta plus 1, so tan square theta plus 1 is secant square theta, so it will become secant cube theta because power is 3 by 2. So that's it, this is the integrand, but the limit will also change because this is for the variable x. And now we've changed the variable of integration theta. So theta ranges from, see, when x is say 0, so here x is 0, the starting value x is 0. When x is 0, what is the value of theta? That is also 0 because tan 0 is 0, so 0. Now when x is infinity, what is the value of theta? So tan 90 degrees, so that is only infinity, right? Tan 90 tends to infinity, so that means this is pi by 2, okay? So tan pi by 2 is infinity. So this is a range of theta. So let us do this integration here. So r here, r squared, 1 r gets cancelled, so r square gets cancelled. What else? Tan theta can be written as sin theta by cos theta, and this is sec theta. So sin theta divided by cos theta multiplied by secant theta, so that gets cancelled. Simply sin theta. So this is simply, so integral 0 to pi by 2. So k q lambda multiplied by simply sin theta d theta, that's all. And divided by r, 1 r is also there. Okay, so sin theta integration is what? So that is minus cos theta. So this is simply k q lambda divided by r. So if you integrate it, it will become minus cos theta, and it is from 0 to pi by 2. So yes, substitute the upper limit. So that will become, so cos 90 is 0. So now cos 0 is 1. So that means k q lambda divided by r. So that's all. So this is the required force due to that ring on that entire rod. Do you understand? So first we will find the force due to this ring on the small portion of the rod, and using integration we find the force on the entire rod. Alright, so this is one of the methods of doing this question. Now we'll do this question by another method. So we'll find the electric field due to the rod instead of ring. So we'll find the electric field due to the rod and multiply by the charge of the ring. Alright, so let us find the electric field due to the rod. Okay, so that is a semi-infinite rod. So we know the electric field due to semi-infinite rod. So it makes angle 45 degree with the horizontal. It has two components, one in the vertically upward direction and one in the horizontal direction. So the electric field here is E equals, so k lambda divided by r. This is the horizontal component and also the vertical component. But we only take the horizontal component, no need of the vertical component, because the vertical components anyway get cancelled. So we take the topmost point where it has a vertically upward electric field. But if you take the bottommost point, so there will be a vertically downward electric field. Do you understand? So these two cancel each other, vertically upward, vertically downward. See, all the vertical components cancel each other, right? So we are only left with the horizontal component, so k lambda divided by r. So no need to consider the vertical component, consider only the horizontal component, k lambda by r. Is that okay? Now this is the electric field due to that rod. Now we have to find the force. Force on the charge dq. dq is the charge of the small portion of the ring, only that small portion. So that has charge dq. Now the same formula, what is the force? The electric field multiplied by the charge. So the force here, so that is df, the force on only that small portion. So that is dq multiplied by that electric field, which is k lambda divided by r. Now we can directly do the integration of this. So force here equals k lambda divided by r integration of dq. Okay, df is there, we need to find f, so we just do the integration. But unlike here, we can directly do the integration because all these are constant values, r, lambda, k. That's why we have taken these values out. So we are just left with the integration of dq. What is integration of dq? Simply q, because no other variable. The only variable here is q. So just do the integration. So that is simply k lambda q divided by r. That's all. So this is our required force. So same answer here, kq lambda divided by r. So this is the force between these two charged particles, right? So these two are objects, not point objects, right? Point charges, we can directly use the formula Coulomb's law, right? So if they are not point charges, we have to use the concept of integration. So making use of this idea, right? The force equals the charge multiplied by the electric field. So that's all. So this is why we learn electric field. Sometimes to find the force also, we need the electric field due to the various shapes, right? So we know the electric field due to the ring. So using that, we find the force. Do you understand? That's all. So this is the answer to the question. So k lambda q divided by r. Okay. A rod of length 2r and mass m with charge density minus lambda is symmetrically placed along the axis of a ring of charge q. If the rod is slightly displaced along the axis by a small length, the time period of the resulting simple harmonic motion. So here in this question also we are given a charged ring and a rod, but the difference here is that this rod is a finite length, not infinite length like last question, and also it is symmetrically placed. So that means the portion of the rod on the right side of the ring and on the left side of the ring, they have the same length. So that means the net force acting on this rod is 0, because the portion on the right will experience a force in the positive x direction, and also the portion on the left will experience a force in the negative x direction. So that means the net force is 0, no force acting on this rod. So that means it is in equilibrium. But now we disturb this equilibrium position. We move this rod slightly to the right. So that means this equilibrium position, so that is disturbed. So that means there will be a net force. So that force we have to find. So that will be towards the center, right? Because this rod is negatively charged. So it has charge density minus lambda, and this ring is positively charged. So this force will be attractive. So this force is towards the center. When there is a force towards the center, there will be an oscillatory motion. Okay, because it is a stable equilibrium, there will be an oscillatory motion. For small disturbances, it will be a simple harmonic motion. So we need to find the time period of this simple harmonic motion. Alright, that is the question. Now we slightly disturb this rod. Okay, we move this rod slightly by distance, small distance dx. Okay, we move this by distance dx. Now, so the portion of the rod on the right and left, they are not equal, so there will be a net force. Now can you tell me what is the difference between the length on the right and on the left?
dx.
It is not dx. See, this rod is moved by a distance dx to the right. So that means the portion on the right increases by length dx. Similarly, on the left, that length decreases by dx. So on the right, the length increases by dx. On the left, it decreases by dx. That means the total difference is dx plus dx. That means 2 times dx. Do you understand? 2 times dx is the difference between the length on the right and on the left. So this 2 dx distance is what contributes to the force. Do you understand? So that force is only due to this 2 times dx length. Alright. So let us find the force. First, let us write the electric field due to the ring. Alright. So electric field due to the ring. So the electric field due to the ring at a distance, what is that distance? So that distance here is r, right? So r is the distance. That portion 2dx is at a distance r from the center, right?
But it is r plus dx, right?
See, this dx is very small compared to the length r, because it is a very small disturbance. So dx is very small compared to r. So r plus dx can be approximately taken as r only. So the distance from the center to that portion of the rod is taken as r only instead of r plus dx or 2dx. So just r is the value of x. Is that okay? Now let us write the formula. So E equals, so k q x, but x here is r only, that distance from the center. So x here is r, k q r divided by this x square plus r square, which is r square plus r squared only. So to the power 3 by 2. Do you understand? So this is the electric field where x here is r only. So the value of x is approximately r only. Okay, so let us simplify this. So this will give you the electric field. So that is kq divided by, so this is 2r squared. So 2 to the power 3 by 2, which means 2 root 2 multiplied by r squared to the power 3 by 2. So that is r cubed. but R is there already, so R squared. So that's all. This is the electric field due to this ring at that point. Now we have to find the force on that small portion, so simply multiply by the charge. So what is the force here? The force is dF, remember dF, not F, because only that small portion we are finding the force. So dF here equals the charge multiplied by the electric field. So the electric field is this one. So KQ divided by 2 root 2 R squared. That is the electric field multiplied by the charge of that small portion of the rod. So what is charge? It is a linear charge distribution. So the charge here is the linear charge density multiplied by the length. So what is linear charge density? So that is minus lambda, okay, multiplied by the length. So the length here is 2dx. Alright, 2dx is the length. So length multiplied by the linear charge density. So that will give you the answer. Do you understand? So this is the charge of that small portion multiplied by the electric field, we get the force. Now we want the total force, so we have to do the integration. Okay, so let us find the, let's do the integration here. So that is, so 1 2 gets cancelled, minus KQ lambda divided by root 2 R squared. So if you do the integration of dx, so that will be simply x, right? So I am writing directly. So we just do the integration. So we got this. Now if you observe, the force is proportional to the distance x. So that means it is a simple harmonic motion, or we can write the acceleration if you want. So what is the acceleration? Divide the force by the mass of the object. So that means minus KQ lambda divided by, so root 2 R squared m multiplied by x. So that's it. So this is the acceleration. But what is the formula for acceleration for a simple harmonic motion? That is minus omega squared x. Alright, so minus omega squared x. So comparing these two, we can find the value of omega. So once omega is found, the time period is given by the formula. So the time period equals, so 2 pi divided by omega. So that is 2 pi times omega. So compare this and find the value of omega. So square root of, so omega here. So the reciprocal of that, so that is root 2 R square m divided by, so this value KQ lambda. That's all. So this is our required time period of this simple harmonic motion. Do you understand? So that's all. So just like the last question, we found the electric field due to the ring and then multiply by the charge of that small portion. So that will give you the force on that small portion of the rod. Now by integration we get the total force. That's all. So the total force is proportional to x here. So that means it is a simple harmonic motion. So we have the formula for the simple harmonic motion, time period. So using that, we found the time period of this simple harmonic motion of this rod. Okay, so that's it. The electric field due to hemispherical shell of charge density sigma and radius r at its center is. So here we need to find the electric field due to a charged hemispherical shell. So this is a shell having surface charge density sigma. So surface charge density is given instead of the charge. But what is the relation? It is just like the linear charge density. What is linear charge density? So lambda. So that equals the total charge divided by the length. Linear charge density, right? That is the charge divided by the length. Similarly, the surface charge density is the total charge divided by the area, because it is a surface. So we don't talk about the length. We talk about the area. So the surface charge density is the total charge divided by the area of the surface. Or if you want to find the charge, you can multiply the surface charge density by the area. So if one of them is given, you can write the other one. Alright, so the surface charge density is given to be sigma. Now we need to find the electric field due to this hemisphere at the center. Okay, so we will consider a small portion of this sphere. Okay, it is in the shape of a ring. So only due to this ring we will find the electric field. Now if you do the integration, we will get the electric field due to the entire surface. Do you understand? So this is a very small ring. Do you understand? The thickness is very small. Okay, so let us consider the electric field due to this ring. So that has a formula, right? Electric field due to a ring. So let us consider that end of the ring to be making angle theta with the horizontal. So this angle is taken as theta, and the thickness of this ring, right, or the breadth of that strip, so that makes angle, or that subtends angle d theta at the center. So this angle is theta and that thickness subtends angle d theta. Alright, so that means what is the radius of that ring? So that is that length, right? Radius of that ring. So using trigonometry we can find r the projection. So this length is r cos theta. R cos theta is that length. Similarly, the vertical projection r sin theta. So this length is r sin theta and that is r cos theta. So we have all these lengths. Let us find the electric field due to the ring. Okay, but before that, let's first find the charge on this ring, right? So to find the electric field, we need the charge. So let us find the charge on this ring. All right. So let us find the charge on the ring. So the charge on the ring is denoted by dq because only for a small portion, right? dq. So that has value. What is charge? The surface charge density multiplied by the area. So surface charge density multiplied by the area. So area of that ring is what we need to find. So that looks like a cylinder, right? Not exactly, because that portion is curved, not straight. It is curved, but for small value, small thickness, we can consider this to be a cylinder, right? So what is area of cylinder? So that equals sigma multiplied by, so that is 2 pi r h, right? 2 pi r h. So that is the curved surface area of a cylinder. So r is the radius of that cylinder or this ring, and h is the height of the cylinder. That means that thickness. Okay, that means the breadth of the strip. Okay, so let us find it. So this equals, so sigma 2 pi r is the radius of that ring. So that is found here, r cos theta, and the height. So the height is the thickness. So how to find that length? So we need to use this formula from trigonometry. See, there is an arc, okay, radius is r, which makes angle theta. What is length of the arc formula? The length of the arc formula is r times theta, right? So this is the formula. So length of the arc is the radius multiplied by the angle subtended. So this formula we are going to use. So that means 2 pi r cos theta multiplied by the height. The height is the length of the arc. What is length of the arc? R multiplied by the angle subtended. That angle is what we have taken as d theta. So this is the charge on the ring. So we found the charge on the ring. Now we will find the electric field due to this ring at that point. Alright, so let us find the electric field. So the electric field due to the ring. So that is denoted by this dE, okay, because it is only due to that small portion, ring. So to find E, that is the electric field due to the entire surface, you have to do the integration. What is the formula for the electric field due to ring? That is kqx divided by x squared plus r squared to the power 3 by 2. Alright, so but the q here is the charge dq, the charge on the ring, so that is dq. So q is the charge on the ring, so that is denoted by dq here. So k dq multiplied by x. X is the distance of the point from the center of the ring. So that x is here r sin theta. So that we substitute here, r sin theta divided by x squared plus r squared. X here is again r sin theta. So that is r squared sin squared theta plus r squared. But r there is the radius, right? Radius of the ring. So the radius of the ring here is r cos theta. So that has value r squared cos squared theta here to the power 3 by 2. Is that okay? So that's all. Now we have to simplify this after substituting this dq value here. So what do you get? So k dq here is sigma pi 2 cos theta d theta. See here this r value, r times r squared again r cubed. So we have in the numerator r cubed. In the denominator we have this sin square theta plus cos square theta, that is 1 r squared to the power 3 by 2, because the other value gets cancelled, sin squared plus cos squared, that becomes 1. So r squared to the power 3 by 2, that is r cube, and in the numerator also we have r cube. So r cube gets cancelled. Alright, simply 2 cos theta d theta multiplied by sin theta. So sin theta d theta. No denominator because r square gets cancelled. Okay, that's all. So this is dE, but we want to find E, just do the integration. Okay, so E. So let's simplify this first. K sigma pi. Now this 2 sin theta cos theta can be written as sin 2 theta, right? That has a formula, right? So sin 2 theta is 2 sin theta cos theta. So this can be written as sin 2 theta d theta. Alright, so that you have to do the integration of, see, the range of values of theta. So that is from 0, because 0 is the starting point, right? So theta is 0 to pi by 2. Okay, at the topmost point the value is pi by 2. Okay,
It's a hemisphere, the angle must be 180 degrees.
no, not 180 degrees, only 90 degrees. See, even for this acute angle theta, it covers the entire region, not only the portion on the right, it also covers the portion on the left also. If you take theta from 0 to 90, it will cover the entire hemisphere, not necessarily 180 degrees. 0 to 90 itself will cover the whole region. Do you understand? So 0 to 90, so that is the range of theta. Okay, that's it. Now we'll do the integration of this. So this is k sigma pi, so sine 2 theta, so that has integration, so minus cos 2 theta divided by 2 from 0 to pi by 2. So if you do the simplification of this, so cos 0 is 1, okay, 1 by 2, and similarly pi by 2, if you substitute cos pi, cos 180 degrees, so that is minus 1, so that will become 1 plus 1, 2 divided by 2, so that becomes 1. So simply the answer is k sigma pi. So that is our required electric field due to the hemispherical shell. Do you understand? So k sigma pi is the electric field due to hemispherical shell at the center. Alright, the sigma here is the charge density. We can also write it in terms of epsilon 0. See, k value is 1 divided by 4 pi epsilon 0. So that can also be substituted here. See, whenever there is a pi, we usually write the answer in terms of epsilon 0 because the pi will get cancelled, right? See, this is simply, see, the value of k is 1 by 4 pi epsilon 0 and sigma pi. So this pi gets cancelled. So we get simply sigma divided by 4 epsilon 0. So that's all. So this is the answer. The electric field due to the hemispherical shell, okay, at the center. So that has value sigma divided by 4 epsilon 0. Okay. A large sheet of charge density sigma has a circular hole of radius r. An electron on the axis of a circle at a distance 2r is given an initial speed v away from the sheet, where v squared equals E sigma n divided by m epsilon 0 multiplied by square root of 2 minus 1 times r. If it reaches a maximum distance of 3r from the plane, then the value of n is. So here we have an infinitely large plane, but it has a circular hole. There is an electron which is given a velocity in the forward direction. It stops after a certain distance. Now we need to find the initial velocity. Alright. So what is electron? It is a charged object, right? So that will experience some force due to this charged plane. So that force we have to find. So we have an electric field. From that we can find the force. From force we can find the acceleration. From acceleration we can find the velocity. So that's what we are going to find one by one. So first let us find the electric field due to this object, charged object, right? But it is not a standard object because it is a plane, but there is a hole. So what we have to do, we will first find the electric field due to that plane and we'll subtract the electric field due to that hole. So that hole is in the shape of a disk, right? Circular disk. So we will find the electric field due to the plane, subtract the electric field due to the disk. So that will give you the total electric field due to that plane. Is that okay? Yes. So this electric field due to that infinite plane. So that has the formula sigma divided by 2 epsilon 0. That is electric field due to the plane. From that you have to subtract so the electric field due to the disk. So that is removed from that. So that is sigma divided by 2 epsilon 0. 1 minus x divided by root x squared plus r squared. So this is the electric field due to the disk. Alright, so that is removed from this total electric field. Alright, yes. Now let us simplify this. So this equals, so this value gets cancelled. So that becomes simply sigma x divided by, so 2 epsilon 0 multiplied by, so root x squared plus r squared. Okay, so that is electric field. But electric field is what? That is the force divided by the charge, right? Electric field is force divided by the charge. The charge here is the charge of an electron. So that is minus E. The charge of an electron is minus E. So force divided by the charge. So that is electric field. Okay, done. Now, what is this force? Force can be written as mass times the acceleration. Okay, mass times the acceleration. But what is acceleration? The rate of change of velocity. So dv by dt. So that equals, so this is cross multiplied. So it is minus E sigma x divided by 2 epsilon 0 square root of x squared plus r squared. Alright, so the force is written as mass times the acceleration. Okay, but there are three variables here, v, t and x. Let's convert into two variable question, then only we can do the integration on both the sides. So m, So dv by dt can be written as dv by dx multiplied by dx by dt, right? Like the chain rule. So dv by dx times dx by dt, that is same as dv by dt. So this value equals that thing, so minus e sigma x divided by 2 epsilon 0 square root of x squared plus r squared. Okay, now so dv by dx by dt is same as the velocity, right? So that is the rate of change of displacement, so that is the velocity. So m multiplied by this is v, so v dv, so that equals, so this is multiplied there, so minus e sigma x dx divided by, so 2 epsilon 0 multiplied by x squared plus r squared. Okay, so let us do the integration now. So let's do the integration here. So if you do the integration, so v initially was 0, right? So initial velocity is v, not 0. The final velocity is 0 because as the object reaches the maximum point, right, the maximum distance, it will stop, which means it will start to return. So that is when the velocity becomes 0. The final velocity is 0. Initial velocity was v, right? So that is given initial velocity v. Okay, now here the right hand side. So integration of, so what is the initial value of x? It is initially at a distance 2r and it reaches a distance 3r. So that's all. So just do the integration, you should be able to get the answer. So this becomes, okay, so this integration is v squared divided by 2. If you substitute the upper and lower limits, so it will become, so minus m v squared divided by 2. So that equals, so how will you do the integration of this? These are all constant values, you can take out. So minus e sigma divided by 2 epsilon 0 multiplied by, how will you do the integration of this? So I will write this value directly, right? So the actual method is x squared plus r squared should be taken as t, right? Substitution method, because the derivative of that is 2x dx, which is already there, 2x dx, at least x dx is there. So let us take the substitution t equals x squared plus r squared. But if you do the substitution, you will get this value. I'm writing it directly. So this will become, so this is taken as this is taken as t, so x squared plus r squared. So it will become 1 divided by root t dt. So that will become square root of t, which is square root of this x squared plus r squared. So this is the integration. Now we have to substitute the limits. So if you substitute this limits like 2r to 3r. Okay, so substitute this 3r here. So what will it become? So it will become 9r squared plus r squared. So 10r squared. So square root of that means root 10 multiplied by r. Similarly, if you substitute the lower limit, it is 4r squared plus r squared. This means 5r squared root. So that means root 5r. So that if you simplify, so we'll get the value. So this value is, okay, let me write it again. So minus mv squared divided by 2. So that equals, so minus e sigma divided by 2 epsilon 0 multiplied by, so this will become, so root 10r. So r multiplied by root 10. So this if you substitute, it will become root 5r. So root 5 here. Okay, so that will give you the value of v squared. So v squared here equals, so 2 gets cancelled, m is divided. So it is e sigma divided by m epsilon 0 multiplied by r. So from this you can take root 5 out. So that will become root 2 minus 1. So that's all. So this is the value of v squared, that is the initial speed. Alright, so you compare this with the expression given in the question, we can get the value of n. So that is root 5. Okay, so root 5 is the value of this n. Okay. Two infinite long static line charges of constant positive charge density lambda are kept parallel to each other. A charge q kept in the middle is given a small displacement perpendicular to the lines towards one of the lines. Then, alright, so this is not exactly the JEE advanced question, it is slightly rephrased to suit our needs, but essentially the same question. See, there are two lines of charges. Alright, so these two lines of charges, they have some electric field, alright, at the center. Now this line will have electric field in the forward direction and that will have electric field in the opposite direction. These two electric fields will cancel each other, which means there is no net electric field at the midpoint. You understand? So that means no force acting on the charge q. So the charge q is in equilibrium. But is it in stable equilibrium? Stable equilibrium means if you slightly disturb this equilibrium position, it will try to get back to the original position, which means the force will be towards the center. If the force is not towards the center, away from the center, it is not in stable equilibrium, there is no oscillatory motion. When the force is towards the center, there will be an oscillatory motion or simple harmonic motion. So let us see whether the force is in the negative direction or positive direction. Alright, so let us find the total force. Let us first find the total electric field due to these two charged objects. Alright, so let's find the electric field due to these two lines of charges. So E equals, let us first find the electric field due to this first rod. So that is at a distance. See the distance between these two rods, so that is taken as say 2a. Let us take it to be 2a. Now if you move the charge q by distance x in the forward direction, positive direction, that means the total distance between the first line of charge and that charge q is a plus x. Right, so the total distance is 2a, so half of the distance is a plus x is the distance. What is the formula for the electric field due to infinite line of charge? So that is 2k lambda divided by the distance, but that distance here is a plus x, so that is the electric field. Now similarly, so what is the electric field due to the other line of charge? So that is minus, right, opposite direction, minus this direction, minus, so 2k lambda divided by, so that distance is a minus x because it is closer by a distance x, so it is a minus x. Okay, so let us simplify this. So this is simply, so 2k lambda, so this is a minus x minus of a plus x, so that will become, so minus 2x divided by, so this is a squared minus x squared. Okay, so this is the electric field. Okay, we found the electric field. Now we need to find the force. How to find the force from the electric field? So force equals the charge multiplied by the electric field. That's all. Charge multiplied by electric field will give you the force on the charge q. Okay, so charge multiplied by this, what will that become? So that is, so minus 4k lambda q divided by a squared minus x squared multiplied by x. Is that okay? So that's also, this is the force. Okay, now it's given that x is very small compared to a. It's a slight disturbance only, right? Otherwise it won't be a simple harmonic motion. X is very small compared to a, which means we can take the x value or a squared minus x value approximately equal to a squared only. Alright, so we take the approximate value of a square because a square is very big compared to x, so that means this subtraction does not make much of a difference. So a squared minus x squared can be approximately taken as a squared only. So this value equals minus 4k lambda q divided by a square multiplied by x. So that's all. So that is the force which is proportional to the distance. That means it is a simple harmonic motion. For small value of x, it executes a simple harmonic motion. So that's all. So force is minus 4k lambda q divided by a square times x. Okay, but this force has to be negative. Okay, we want the force to be negative, then only it will be towards the center. So when will this force be negative? See, all these values are positive, but we don't know about charge q. Okay, the charge q, what if charge q is negative? If the charge q is negative, already there is a negative sign, so negative, that will become positive, force become positive, that will be in the forward direction then, not towards the center. So for this whole expression to be negative, so we want the charge q to be positive. Okay, for q to be negative, for the charge force F to be negative, the charge q must be positive. Okay, so that's all. So if the charge q is positive, it executes a simple harmonic motion, otherwise no oscillatory motion. Alright, so that's all. So that is the answer to the first question. Okay.